All right, sounds good.
Okay, so I'm here with Zohar again, talking about physics, in particular, whatever, Gary physics. And so let's see how things go about what is understood and not understood, or what he might disagree or contend there might be some other answer or whatever. So,
I feel like I might just call this like a tutoring session because you're basically just teaching me.
could be. Yeah, could be the way it turns out. See how it goes.
Okay. So are you on the whiteboard?
It can be, or I can use the chalkboard, either one.
Okay. So I guess I'll use the whiteboard and then you could use either one.
Okay.
So for the simulation, like there's this weird thing that ends up happening. So I just wanted to ask you a few questions about like electron versus electron repulsion. I guess I'll draw it in blue. So if you got two electrons so an electron's radiating this blue force, like if you're close to an electron, you're going to see a lot of blue force coming towards you, right?
Well, the idea is it's a perfect reflection. So when the same color force hits the same color object, it's a perfect reflection.
Is it
And
always perfect, or is there like a chance of it not being a perfect reflection?
yeah, sorry, I just got to get this volume right. It's going. It's too loud, too soft, whatever. What'd you say?
Is it always a perfect reflection, or should there be like a chance that it might just go right through it, or it might like not be a perfect reflection?
No, I don't think there's any chance of that. So I think it's yeah, it always reflects. Um, there could be questions about, the whole thing could be just a pattern in space, and so where exactly it reflects could be different places. But the idea is that it's the stuff inside is moving technically very little space back and forth inside the electron, you could say. So if you thought of the electron as just having an arrow that was going back and forth very fast, that's causing an external pressure. So if there was little walls around it, it would be hitting those walls constantly at that speed. And the idea is the external universe hits it at the same rate, and that's why it stays a certain size. It's because the external pressure is exactly the same as the internal pressure. The two of them are
Yeah.
balancing each other out. So the idea is when you're causing a change to that pressure, then you're changing how fast the little thing inside is moving, and therefore not moving, but how many interactions it has, and therefore it moves. And you know, but
So did you show like we could show like the R squared rule in a simulation, for example? Like we can have the two objects, the two electrons, kind of like at one distance from each other of like R, and then we can have another distance from each other in like another simulation where they're like a bit farther away, like big R. And then do you think we could like maybe look at the numbers of like keep track basically of how many collisions there is between the two
well,
electrons?
the R rule, it's the R rule in charge. So charge is obeying the R rule close in. So it's not the R squared rule anymore. So the
Oh,
truth is that you go half the distance, you get twice as much energy. You go, so it's. Let's see, this volume still doesn't change. Yeah, I can't change the volume for some reason. All right. Sorry, I'm just trying to get the volume right. It's still a little too loud here, but let me try the speakers down. Okay. Um, so the idea is it's a ping pong paddle argument. Okay, so there's a ball trapped between two paddles. If I bring them twice as close, there's twice as many impacts. I bring them twice as far apart, there's twice as few. So it's the R rule. It's not the R squared rule. It's only the R squared rule when you start radiating to the whole universe. But when two electrons are communicating to each other, there's an R rule. When it's a magnet, it's the R cubed rule. So I mean, there's more than one rule depending on whether it's a dipole, a monopole, or whether the two bodies are really close to each other.
okay. I was also wondering, like, if there's blue force bits that are coming like in between the two electrons, isn't that kind of similar to like light hitting an electron? Because like the blue force bit is going back and forth, right? So it's kind of like hitting the electron at a frequency. Would you
No,
say
I mean you have
that?
to send it at a frequency for it to hit it at a frequency, and photons are really huge. Photons spread out over thousands of atoms worth of distance. A photon's polarization is thick. And an electron is a tiny thing, so one photon couldn't possibly hit one electron. Photons have to act collectively on a material. That's why metals are crystals and glass is a crystal, because the crystal is vibrating and that's sending the same pattern to the other side of the glass. But it requires the entire crystal to react to the photon, not just one electron.
So I guess like when you draw light, you usually draw it like this, like electron force in a frequency. But in like 3 dimensions, it would be more like big sheets that are at a frequency.
No, it wouldn't. No. They're tiny little dots. They're not. They have no size. The quanta is a tiny little thing in space. Tiny little ball. It's like BBs and oranges. So you have a box full of BBs that are bouncing in all directions, and then you put some oranges in there, and that's the proportions, really. The electron is huge compared to the photon. It's a little tiny speck flying through space, and the only thing you're doing is it's like bullets. If I shoot a gun, right, pointed at the camera. Now, I can shoot right at the target, but if I move the gun each time I shoot a bullet, then each bullet will be on a slightly different path. They'll all be parallel, but each bullet will be in a different place in space, and that's the polarization, is how much did the gun move when the bullets were being fired.
So are you saying that, because I was thinking of it more of like a gun that's shooting like 10 bullets at a time.
No,
so
there's no need to have 10 at a time.
Well, I mean, like let's say you're shooting like the color of light that's red, let's say, so like red colored light.
It's just a frequency. So all the color means is how far apart are the bullets. If they're really close, then it's blue light. The bullets are a little further apart, it's red light. That's it. It just has to do with how far apart the bullets are.
Yeah, but the light is usually spread across like a surface, kind of like that's a bigger surface. So wouldn't it be the same frequency all across that surface? So let's say like you shine the flashlight at a wall.
No. I mean, you have to hit it with individual patterns, so you have to hit it with rows of guns. So you have more guns, you can shoot more photons. But one gun shoots one stream of bullets. One gun doesn't shoot a whole bunch of bullets. So you have to shoot it off of, again, if the whole crystal is moving, a crystal could be thousands of atoms across. If the whole crystal is moving into space to change the dimension, so when there's a pressure and you move something, well then it hits the thing sooner, and that creates a frequency because everything gets collected by that movement and they all get thrown off at the same time. So the idea is that it's like you're just catching and throwing, and but the idea is it can only be caught by a surface, a crystal. The crystal does the catching, and then it throws back everything it caught.
Okay, so I guess let's go back to the electron repulsion then. Like, what evidence do we have that it is R squared or that it is R? Like, I feel like once the electrons are really close to each other, we don't really have a way of knowing.
Yeah, well, none of those rules, none of regular Maxwellian mechanics it's always under the condition of these restraints. It doesn't work, okay, between electrons. It doesn't work even between two surfaces. If I put them really close together, I break all the rules because I create essentially an infinite surface. From any one electron's perspective, the other surface looks infinite because I'm so close to it. So almost every angle, I'm still going to hit the other surface, so I can't miss the other surface. So in a sense, all of Maxwell's equations have nothing to do with really close things. When things are really close together, the math doesn't work. When things are really, really far apart, the math doesn't work.
I guess, but like once we get the simulation, it should still work really far apart, but then we can just say that it's not.
It's not by the R squared rule. I'm just saying there's no law that says R squared. R squared is a consequence of spherical objects. Spherical objects create the R squared rule because it just has to do with the fact that a sphere gets bigger, 4 times bigger, every time I increase the radius. I double the radius, I create 4 times more circumference.
Okay,
So
you're talking about
that's the
speed.
idea.
Okay.
So anything that radiates in every direction, in all 360 degrees in both dimensions, anything that radiates like that is going to be obeying the R squared rule.
Yeah, I get that. So that makes sense, I guess. But then doesn't that mean that the electrons should obey the R squared rule when they're close to each
I'm
other?
just
Or
saying. Well,
does it have,
how can they obey the R squared rule when they're right close to each other? They're no longer seeing each other as a sphere.
okay, I see what you're saying. Yeah, it's the same with gravity, right? Like it's only R squared kind of far from Earth, so then maybe.
Well, I'm just saying the closer you get the thing to something else. Well, gravity is completely different because gravity isn't based on this idea of a ping pong paddle and the force caught between it. It's based on the fact that you absorbed a whole bunch of momentum as you were moving. You absorbed force, so you're collecting it as one object moves towards another object. This object collected a whole bunch of energy. That's how come it's moving. It's because it collected it. And when it shows up here, yeah, it's going to explode. It's going to do all that energy gets released. So it's a storage argument. Gravity is because energy is stored.
Okay. I guess that should be good then. What else was I going to say? I guess if there's yeah, I'm not sure if I have much else to talk about, to be honest.
Yeah, well, I guess you could, I'll just draw this real quick, just so you understand what in comparison to, photons. Just to understand that an electron, the photon has bits that are here, here, here. They're really, the spacing is huge. So the spacing of the photon, that is the difference between where the bullets are in space, right? I mean, I could draw them as just being a little off, right? But that little bit of off to an electron is millions of miles off. So the electron is so much smaller than the spread of the photon. So the photon is spreading over the distance of 2,000 atoms. So each bit of the photon is hitting, obviously, a very different electron. They can't hit the same electron. They're not like a stream coming right for the electron. It hits it and it hits it and it hits it and it hits it and it hits it. So that's why photons are composites. You have to really send more than one photon to actually get one photon out. So everything we see is really photons are being destroyed. Like when a photon hits the surface, so the bits are coming in, the bullets. Well, one of the bullets reflects. Okay, this other bullet went straight through. This other little bullet went crooked. So it's a composite, and what you're really doing is saying, where did I put a photon back together? Where did I take enough pieces that went straight through, or pieces that reflected? Okay, so I had one piece reflect, another piece off a different photon, another piece off a different photon, and those pieces actually added up back to the right frequency. So you're really not, whenever a photon is interacting with a surface of any kind, it's always being broken, and then all you're doing is saying, where did I put them back together? And so when you put this, so there's no like red photon that goes into the surface and red photons does something different. All these little bullets are exactly the same, and all they have is a frequency, and all you're trying to do is put the frequency back together. So when you have constructive interference, what you're really just saying is a little piece of a photon broke off from here, and a little piece broke off from here, so that was this one and this one, and now you're putting them back together again in the proper frequency. And so this is a one full wavelength of different distance. So you really just took pieces from one photon and another photon and just put them back together again. You took the first two clumps of one photon and then the last two clumps of another photon, and you're making a photon out of two different photons. If you get me.
I think I got that.
Right. So they
cool.
never destructively interfere. You only break them and then remake them.
Is that why, like, if sunlight is kind of white, right? But like if it hits a leaf, then
Well, it's not white. It's made up
green.
of all the colors. So it has red beams in it. It has blue beams in it. It has green beams in it. So it has
Okay.
all those colors in it. But so that's why you can separate them out. But you're not like I said, the surface doesn't care. When each electron doesn't care whether it was hit by a blue one, a red one, or a green one. It doesn't know because it's only getting hit by one bullet. And bullets all move the same speed and are all exactly the same. And so it is the surface of the material that interprets that as a photon and then transfers that energy. So it's like the atoms are tied to each other, creating a crystal. And it's this whole crystal.
But I think
The whole crystal is what transfers the energy. The crystal moves because you hit it with enough energy to move it collectively.
So I think your whiteboard is kind of off the screen. Maybe move.
Well, there's a blackboard, but whatever.
Oh, sorry.
Yeah, well, I just was saying, it wasn't a big deal, but I'm just saying the photons hit a surface and the surface interprets them and then re-admits them. So it's the crystals just passing on the information from one crystal to the next crystal to the next crystal, and then it pushes the external world in exactly the same shape as it was pushed. So it was dented a certain way. You know, the photons hit, the little bits hit and made a certain kind of dent pattern. The dent pattern will be transmitted by the crystal, and it'll create the same dent pattern on the other side. And then when the external universe hits that, the reflection will be exactly the same as what went in. So what went in is a texture, and a texture will be created on the other side, and that texture will create the new photons.
Okay, that kind of made sense, but I probably have to rewatch this.
Yeah. All right. Well, I just want to be clear that individual photons don't interact with electrons. Just the tiniest pieces, the clumps of photons do. And the atoms are the ones that have to create something that's transparent, that some idea that they're going to transmit the entire photon through. So, and the rest of it's just a phase change. So you could sort of understand that if there's just an oxygen atom, the photon, one piece of the photon could miss the atom, and the other piece of the photon hits the atom. And so one piece of the bullet, one of the bullets might be a phase out of phase, knock the phase out of phase. And now the photon is invisible. But if it happens to more than one of them, you can see that the out of phase part can be fixed because you're combining two photons that were broken.
Yeah. So I guess maybe we should talk about the single slit again. Is there any difference between the single slit experiment and the double slit experiment? Or are they the same thing?
Well, they're obviously different in the sense there's four surfaces in one of them and there's only two surfaces in the other one. So that's one obvious difference. But the difference really is whether you're talking about external surfaces. See, I could put a single impediment somewhere and then the surfaces are their free universe is out. So the electrons aren't being compressed, right? So that you could figure the electrons go further out when they don't have another surface next to them. And then when you have a slit, you have exactly the opposite circumstances where these electrons on this side hate the electrons on this side. And so the electrons are being compressed into the surface. So that's the difference between the two surfaces. On this surface, the electrons are free to go out. And on this surface, the interior surface, the electrons are compressed into the surface. So the two kinds of the electrons are in different pressure depending on whether you're on the inside and the outside. So when you make the two slit experiment, bad glare there. Well, that's the sun. Can't do much for that because that's the sun. So anyway, so the two slit is just a combination of the two, the single open slit and the wall. So there's electrons going out here and out here, and there's electrons going in on this surface and in on this surface. So they're under different pressure, and both of them are going to shoot bits this way and this way, this way, this way, this way, this way, and this way, this way. So they're all going to, for each electron the little bullet hits, it gets bent, say, 3 degrees. So if it hits 3 electrons, it goes 9 degrees. If it hits 2 electrons, it's 6 degrees. If it hits 1 electron, it's 3 degrees. So depending on how many electrons it hits, it tells you how far it's going to get pushed over. And the rest of it is just adding up the difference in the phase. The difference between a piece from here and a piece from here combine, and that will create another new photon. and it's going to be blue or red or green or some other color. If I put white light in with green, red, and blue, then each one will end up lining up where the phases are one wavelength different in distance. So it's really the difference in distance of where the pieces came from that'll dictate what color you see. But it's just pieces, and each piece gets moved based on how many electrons it hits. So the photons get totally annihilated going through the slit, and you're just remaking new photons on the other side.
So is it? I think there's no internet connection. Does that mean you can't see me?
There's what?
For some reason it says no internet connection for me, but I guess there is.
I'm still here, still moving, so...
Okay. So is the angle that the photons get deflected, does that angle have to do with the frequency of the photon?
No. As I stated, each photon is just made out of the same bullets. The bullets go the same speed, and the bullets are all identical. And the only thing you change is the distance between them. And the surfaces have no idea what the distance between them is, because each electron only deals with one bullet. It doesn't deal with the whole string of bullets. It just deals with one bullet out of the bunch of bullets the gun fired. So it has no idea whether a blue photon is hitting it or a red photon. It doesn't give a damn. It's always going to just send it in a direction. And like I said, what color they end up being just has to do with where they're reconstructed and the different phase angles. So all you're doing is putting the bullets back in phase.
Okay. I think I learned a lot today already.
Okay. All right. Well, keep it short and simple and sweet and all that crap. So.
Yeah, maybe let's just make it short, I guess. Definitely, I didn't realize that the sun is just shooting out photons at different frequencies, and then when you just combine them all together, it looks like white.
Yeah, and likewise, when you put different colored photons in, you can only get them back at certain specific places where the wavelength, the distance, the extra one has to travel a longer distance. That distance has to be exactly the wavelength of the pieces you're putting together. So now you can put two different photons together and realign them because you're changing the phase.
Yeah, but they have to be the same frequency, right?
Well, I'm just saying that the little bullets this doesn't matter. I'm just saying the only place you can put blue ones together is here. This is the only place the angles will be right. So you'll only get a blue one. There's lots of blue pieces. Blue pieces are going everywhere. Okay, they're going here, they're going here, they're going here, they're going here. But you can only put a blue one together here, here, and here. At certain specific locations is the only place the phase will be right. So you can't reconstruct a blue one in the wrong place. And you can't reconstruct a red one in the wrong place, even though the pieces are going all those places. So the empty spots have plenty of broken photons hitting them. It's not like energy isn't hitting all the dead spots. The dead spots are getting hit with a ton of energy. They're just not getting hit with something we see as a photon. A frog sees photons we don't see. So, right, a frog could be sitting next to me. He sees a whole bunch of photons I don't see. So they're still hitting me, right? They're still going into my eye. They're going hitting my retina. But I don't recognize them as photons because they weren't long enough. There wasn't enough ray of them. There wasn't enough bullets. So I don't see it. But the frog would see it.
Okay, because their eye is more sensitive to them.
It can see a smaller ray length. So it can see a photon that's broken to us. It's fixed to him. And so that's all we're really talking about is where did you fix the photons? So if he looked at the pattern, he'd also see more photons. Because there'd be places where, yes, it wasn't the right ray length, but the photon was made there. So everything he's going to see more of because he'll be reconstructing more photons that are visible. They're still being constructed. I'm just saying there's still photons hitting the dark spots. It's just that they're broken. They don't have the right ray length or they're out of phase. And so we can't see them as a photon. We can't interpret them as a red or a green or a blue. It's like they have more than one frequency built into them, right? So if I made a photon that was, this distance and then it was this far apart, and then there was one, this close. I mean, if I break the frequency, it's not a photon. You can't see it. But the quanta is still there. The energy is still there. It's just in the wrong sequence, and so it won't cause the crystal to move, and we won't see it.
I guess, like, will we feel it at all? Like, will it make us...
Well, I would argue that it is heat. So I would argue that if you did the two-slit experiment and you used temperature sensors instead of photodetectors, and you just found out how much temperature is hitting all the locations, you'd find out it was dead even. There wasn't anywhere where there was more temperature and less temperature.
We have to do that experiment.
Yeah. You need something very sensitive. That's the only problem. Photons are very little amount of energy. They don't have much energy in them. So that's the only downside, is you have to have a very sensitive thermometer.
Yeah, I feel like it's pretty doable, though.
Yeah, I would think it is. So I agree. It's on the list of things to do.
Have you done experiments before? Like, I haven't.
Well, yeah, no, I haven't yet done anything. I just thought of it 3 weeks ago. So, and I thought of using thermocouples, but you got to buy a lot of thermocouples.
Yeah, and like you're not really getting paid for it, or you don't have any resources.
Well, yeah, you have to be kind of. You don't want to buy something that won't work, so I have to do some research into different temperature sensing devices to see which ones are the most sensitive over a broadest range of space.
And then you just like take two surfaces kind of and just put them close enough together.
Well, I'm just saying, if I use thermocouples, I can just put one next to the other, next to the other, next to the other. I can fill a 10-inch space with 100 thermocouples, and so then I'll know that every location almost is covered. And I just sense the temperature at all the locations, and they should be just as hot where it's dark as they are where it's light.
Yeah, that would be kind of interesting, because like you would think that more light means more heat, but then it isn't.
Yeah. Yeah, I think that would prove that the energy is still going to all the locations, and all we haven't done is put photons back together in the locations that are dark. There's still energy there, it just isn't in a form we can see.
Yeah, I think I've also understood something you told me, like, I think in our interview, like, last one, or maybe the one before that. But so, like, the Earth isn't actually, like, there's not more force bits going into the Earth than there is going out of the Earth, right?
Right, it reaches thermal equilibrium, but that equilibrium has to constantly be fueled because the actual motion of the crap inside the Earth, the magma moving, has to be constantly fed by absorbing momentum. So all momentum might look like you're not pushing it anymore, like you pushed it once and it goes forever. But in the real universe, that's not true. Electrons and protons don't do that. So you have to keep feeding any motion. So actually, when the magma is swirling, it's actually consuming force in the both directions.
Okay, that makes sense. Yeah, I guess that's pretty much it. But maybe we should have a bit more interviews and just make them smaller.
Well, it's okay either way. But okey doke. So till the next time and such. And people could ask questions also and whatever. So, but good enough. So till next time.
All right. Sounds good. Thanks. See you.
Yep.